Consider a political discussion group consisting of 4 Democrats, 8 Republicans, and 2 independents. Suppose the 2 group members are randomly selected in succession to attend a political convention. Find the probability of selecting an independent and then a Republican. All right, the probability of getting that first independent, there are 2 independents out of a total of 14 people. Now, what's going to happen here? Once you have selected that independent, you no longer have 14 people to choose from. You only have 13. But how many Republicans are there? There are 8. We are assuming we got that independent on that first pick, therefore it did not affect this right here. All I have to do now is arithmetic, reduce this, multiply this up, and this is 8 over 91. A single die is rolled twice. Find the probability of rolling an odd number the first time and a number greater than 3 the second time. Let's write out our sample space for a single die. So, find the probability of rolling an odd number the first time. Odd, 1, 3, 5. So that's 3 out of 6. And, that's why we're going to multiply, a number greater than 3 the second time. Did this influence what's going to happen on this next roll? No. So we're just looking at this separately. A number greater than 3, 4, 5, 6, that's also 3 out of 6, which you can reduce each of these to 1/2 right now, or use your calculator, whatever works. So the chances of that happening is 1 over 4. An ice chest contains 6 cans of apple juice, 8 cans of grape juice, 4 cans of orange juice, and 2 cans of mango juice. Suppose that you reach into the container and randomly select 3 cans in succession. Find the probability of selecting mango, then grape, then orange. We are picking these in succession. It will be a multiplication situation. But once you pick a can, you're not putting it back. So the probability of getting this first mango is 2 over 20, because if you add this up, you're going to get 20 cans. Once you have taken out that mango, there's only 19 cans left in there for you. But how many grapes are there? There are 8 grapes. Now how many cans are left? There are 18 cans left, and we want an orange. How many orange are? There are 4. And then this is just arithmetic from here. What I did was 4 into 20 is 5. Then I did 2 into 18 is 9. And if you multiply all that up, you're going to get 8 over 855. So reduce if you want, or just use the fraction bar on your calculator to get 8 over 855. All right, conditional probability. Conditional probability is this: the probability of event B, assuming that the event A has already occurred, is called conditional probability of B given A. And the notation is this: it's P parentheses B with a straight up and down bar A. It's helpful to think of the conditional probability of B/A as the probability that event B occurs if the sample space is restricted to the outcomes associated with event A. I don't even use this formula. What I use is the idea right here. We're going to restrict our sample space to be what has happened with the event A. So let's look at an example which will probably help you understand better than the definition. You are dealt 1 card from a 52-card deck. Find the probability that you will be dealt a heart given that the card is red. So knowing that the card is red, that's what's going to go on the bottom. I know there's 26 red cards. I have restricted my sample space to just be the reds. Then I got to go back and find out how many hearts are there. Well, there are 13 hearts. Reduce that and you get 1 over 2. That's all you have to do with conditional probability, is get your denominator based on what they gave you for A, and then go back and work the B. So let's do a couple more examples. These numbered discs are placed in a box and 1 disc is selected at random. Find the probability of selecting an even number given that a green disc is selected. That says I'm only looking at the greens. I only care about this, this, and this. How many greens are there? There's 3. So you're not even looking at this. This is totally out of the picture. Just look at the greens. Now, what's the chances that you'll get an even. Well, in those greens, how many evens are there? There's 2. There you go, 2/3. Sometimes you have to do this from a chart. We've got the outcome of accidents in a certain state for a recent year by whether or not the driver wore a seatbelt. So find the probability of surviving a car accident given that the driver did not wear a seatbelt. That's the denominator. What's the total for the driver did not wear a seatbelt? Right in this column, 167,675. This is an example where they have done the total for you. Sometimes on these charts, you have to do the arithmetic and do the total. So we're looking at the total of no seatbelt because that's what they told us right there, did not wear a seatbelt. Now, we are restricting ourselves to this part of the chart because that's the no seatbelt part of the chart. The other stuff didn't matter. Now we want to know what's the chance of surviving the car accidents. Well, there you go, 165,517, and that's all you have to do. Another chart, if one person is selected from the population described in the table, find the probability that the person is not widowed. All we're looking at is not widowed. This goes back to the first part of this, the 11.7 video on this idea of not. So, not widowed. Well, I know that the probability of not widowed is equal to 1 minus widowed. So all I have to do is 1 minus the total number for the widowed, which is 15.3 out of the total number of people surveyed, 216.8. And you can type this directly in your calculator if you want, or we can do it piece by piece. This 15.3 over 216.8 is 0.071, and the reason I've gone to 3 decimal places is because that's what the direction said. And then 1 minus 0.071 is 0.929. Now, another way to do not widowed would be to add up the never married, the married, the divorced, add all those up together, and that would be a numerator over 216.8. So that's fine to do rather than use the formula of 1 minus. If one person is selected from the population, find the probability that the person is divorced or widowed. Divorced is in here, widowed is in here. We have our totals. So 14.0 plus 21.5, which is 35.5. out of the total number of people surveyed, and we just divide that out to get 3 decimal places, which is 0.168. So the last 2 examples had nothing to do with dependent or independent. It just went back and used some definitions from before. The previous one used the not, and then this is just our basic or.